Hello everybody, in this video we will be looking at the range and domain for the following functions. Straight line, otherwise known as the linear function, the parabola, which is the quadratic function, the hyperbola, and the exponential. We know that a function is basically a rule. You take input values, a certain set of input values, those would be the x's in this case, you put it in the function and it gives us a certain set of output or y values. You should also know that instead of writing y equals, we can write a function like this, where f of x basically means the same thing as y. It is my output value. So we put in specific inputs, we get specific outputs, and we get coordinates or ordered pairs, which we can plot, and we can visually represent the function. Now, a domain is basically all of the x values or the input values that are used. And a range, that is all the y values obtained from putting in the certain input values. So for short, the range, all the y values, domain, all the x values. Nice way to remember it. If you write the word range like this, you see it's got like a long tail like that, and y has a long tail like that. So range, all the y values, domain, all the x values. And it is important to note that the y values depends on the x values. So the y values that I get out in my function depends on the x values that I put in. If I put in different x values, I get different y values. Here's the summary of the different functions that we learn in grade 10, straight line, parabola, hyperbola, exponential, along with their equation and how they look, generally how they look. Obviously, they will look differently depending on, for example, here the a value, the m value, the c value, the q value, and so on. The b value in the sense of exponential. But this is just a general idea. So if you see mx plus c, something like this, we know it's going to be a straight line function that looks like this. As soon as you see x squared, we know we're dealing with a quadratic function, a parabola, that will look like this. If we are dividing by x, so if x is at the bottom, if it's in the denominator, we know we're dealing with a hyperbola, which looks like this. And if x is the exponent like this, we know we're dealing with an exponential function. I just wrote here, for example, that here the c values in both the straight line and the parabola, those are the y-intercepts, so where the graph cuts the y-axis, so there and there. And in the hyperbola and the exponential, the q value, you might call it something else. You might call it a c value as well. Whatever you call it, this variable here, this one, this plus q, yeah, this plus q, that is the horizontal asymptote. So we'll be going over how to get the range and the domain and how to write it for each of these different functions, starting off with the easiest one, the straight line function. Now, before we get into the specifics of each function, I want to remind you of the following. Functions are continuous, which means we should actually draw them like I've drawn them here, where we have arrows on either end of the functions. You see an arrow there and an arrow there. What this basically means, and the same thing for the parabola, see arrow, arrow, same thing for the hyperbola, and so on. What it means is that the function continues in either of those directions. So I could basically extend this function to carry on that way and carry on that way forever to infinity. Same thing here. This function extends or continues going up. This part goes up, 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 up. It continues going on. And it actually, so in the case of the parabola, it actually ends up going like this, forever and ever and ever and ever and ever. So you can see it's going higher and higher and higher, but it's also going wider and wider and wider and wider. Same thing for the hyperbola. This goes up, 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 up forever and ever. Same thing here, this way, forever and ever and ever. I hope that makes sense. They're continuous, which is why I draw those arrows on them. That's important to know when you're thinking about domain and range. The other thing is, in general, when you're thinking about what's the domain, what's the range, we can look at the x-axis, so domain x. So start at the x-axis. Remember, this function carries on this way and it carries on that way. So we go on the x. For what values, for which x values, where does the function exist? It exists for all of these x values going on and on and on and on and on. And same thing here, it exists for all of these x values going on and on and on and on. Why? Because I can draw the function in a way that it'll continue going all the way that way, all the way this way, which means all of the x values going all the way that way to infinity is included in the domain, and all of the x values going on that way to infinity or negative infinity is included in the domain. So So how do we write this? How do we write the domain for the straight line function? We can write that x is an element of all real numbers, which means that x is all the real numbers going all the way to positive infinity, all the way to negative infinity. Another way to write it, therefore, is x is an element of round brackets, negative infinity, all the way to positive infinity. Just a few things to note if you're going to use the interval notation like this. We write x as an element of, so that's the funny e symbol. If you're doing negative infinity to positive infinity, your negative infinity must be on the left, so it's the smaller number on the left, the bigger number on the right. And when it comes to infinity, we always use round brackets. Round brackets means not including. We don't include negative infinity. We don't include positive infinity. I think a shorter, easier way is to do x as an element of real numbers. That is the domain. Now, what about the range? Remember, range is all the y values. So if the domain of all the x values continue here to positive infinity and this way to negative infinity, the graph is going to continue going up, 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 up. It's going to exist for all the positive y values and all the negative y values. So in the same way, we write the range y is an element of all real numbers. Or again, you can say y is an element of negative infinity to positive infinity. Just take note how obviously for domain we use x as an element of, and for range we use y as an element of. And that will always be the domain and range for straight line functions. What about a parabola or a quadratic function? Starting off with the x values. The x values, remember now the parabola, I know that it only shows on my graph, on my function, to go from where x over here is around like -2 or -2.25 or whatever, to where x is +2. But the graph is continuous. So although on my graph, on my page, on my picture, it looks like the x values start there and end there, that's not the only places where this function exists. This graph is continuous. So it carries on that way, it carries on that way. It actually basically carries on going like this, and it goes like that, and it stretches outwards. So basically, all the x values are included for this function. They can exist for this function. So the domain for a parabola, once again, for this parabola here, is x is an element of real numbers, once again, or x is an element of from negative infinity to positive infinity. You need to be careful, however, for the range for a parabola. If you take a look at this function over here, you can see that it is what I call a happy parabola. It's smiling, and the reason why is because its a value, the equation for this is y equals x squared. The a value, which is the value here in front of the x, is positive. So it's +1. If it's positive, it's happy. If it's negative, it's sad. So because of this, what it means is that my parabola only starts here. So if you look at the y values, do you see that for all the negative y values, this graph, this function does not exist. It will never exist for any of the y values. And you could say, but ma'am, what if I put a negative value in for x? Well, we can try it. If I put in x as -1, so y equals -1 squared, -1 times -1, +1. So there, when x is -1, y is +1. As you can see, the y values are not negative for this graph. So when we are stating the range, it's all the y values, all the output values. It only starts here where y is 0. And then it continues for all of the positive y values to infinity. Because remember, the graph goes on and on and on and on and on and on, but it starts where y is 0. So how do you write this? We can write it by saying y is greater than or equal to 0. Why am I saying greater than and equal to? Because where y is 0, right over here, the function does exist. So where y is 0, the function exists. Where y is 1, 2, 3, 4, all of those y values are included. So basically y must be bigger than 0, or y is bigger than 0. Another way to write it would be like this. Y is an element of, and here this is an interval notation, so from 0, but including 0. So note how I'm using the square brackets for including, because it includes 0. to positive infinity, round brackets when you're dealing with infinity. Let's try this parabola over here, which you can see is a sad parabola. The domain, same thing. X is an element of all real numbers. The arrows, well, there should be arrows here indicating the function continues for all the x values. The range, however, in this case is different. Take a look at the y values. The y values start over here where y is equal to 2. And it carries on for all the y values less than 2, all the way to negative infinity. So how would you write it? Pause the screen, see if you can do it. But you would write it as follows. Y must be less than or equal to 2 because it's equal at that point or less than. Or y is an element of negative infinity, round bracket, to 2, square bracket. Remember, you must always start with the smallest number. So it goes down to negative infinity. Negative infinity is obviously smaller than 2. So small number to the big number, not including negative infinity, but including 2. Taking a look at the hyperbola before we get into the domain and range, I just want to quickly remind you of something. The asymptotes, which very much so affect the range and the domain. So if you look at the general equation for a hyperbola, now again, remember, they might replace the a and the q with other letters, but essentially these variables mean the same thing. It doesn't matter if it's an a or a q or a k and a whatever. The q, that is what we call the horizontal asymptote. So the y equals asymptote. So it's the asymptote that looks like this. So if q is 2, for example, then your horizontal asymptote, the one that looks like this, will be where y is equal to 2. So it'll cut the y-axis here at 2. It'll be a horizontal line going like that. In this case, you can see that it is along the line of y is equal to 0. So in this graph, q is 0. Okay, so q is equal to 0. So the y-asymptote, or the horizontal asymptote, is y is equal to 0. The function does not exist here, okay, where the asymptote is. You can see that the function approaches the asymptote. It gets closer to it, but it never ever touches it. It never ever crosses it. Very important. In grade 10, we talk about the second asymptote as being the vertical asymptote. And in grade 10 over here, we always speak about it as being where x is equal to 0. That is my vertical asymptote. X is equal to 0. The reason why is because if I have to put 0 in the place of x over here, the function becomes undefined. You can't divide by 0. The a divided by 0 is undefined. Can't be. Graph does not exist there. So basically where x is 0, that is my one asymptote that goes down like that. And then my horizontal asymptote is this q value, which in this case is 0, which is this one over here. So when we state the domain and range, we must be careful of these asymptotes because the graph cannot exist where there is an asymptote. So if we're doing the domain, remember, starting with domain, domain's all the x values. Start from the left of the graph. When we read a graph, it's like when we read from left to right. So starting at the left-hand side here, you can see that this arrow is pointing that way. In other words, the graph is going to continue for all the x values to negative infinity. I hope that makes sense. This graph will continue on and 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 on till where x is negative infinity. So it goes from negative infinity, and if we look at this part of the function over here, it goes on and on and on and on and on all the way to where x is positive infinity. So like the straight line, we could say that the domain, so domain, remember all the x values, is where x is an element of all real numbers. But let's go again from the left to the right. So it exists for all these values of x from negative infinity all the way here, all the way here, all the way here, and then we hit an asymptote. You can see that over here, where x is 0, okay, this line over here is the x is equal to 0 line. Now this confuses my students. Why is that the x is 0 line? Because if this is my Cartesian plane, this is the y-axis, this is the x-axis, a line that cuts like this, it's cutting the x-axis where x is equal to 0. So that green dotted line is the line x is equal to 0. The graph does not exist there. The function does not exist there. Therefore, it cannot be part of my domain. So when you state your domain, yes, you can say x is an element of all real numbers, but you have to say x cannot equal 0. Similarly, for the range or my y values, If we go from here, the negative values, you see the graph is continuous, which means it extends to negative infinity. It goes all the way from negative infinity. Then at the horizontal asymptote over here, which is where y is equal to 0, the graph does not exist. But then it carries on. It exists for all the other y values to positive infinity. So in the same way, we can say that y is an element of all real numbers, except y cannot equal 0. Basically, what you would say here is y cannot equal your q value. Remember, this is your q value, this horizontal asymptote. So if q was 2, then the graph would exist for all real numbers, but y would not equal 2. Let's do an example like that. So what makes this function different to the one before is that, again, we have two asymptotes, and sometimes they don't show the vertical asymptote. So you can see here that the function, let me highlight it, the function is approaching the y-axis, but not touching it. Same thing here. The function is approaching the y-axis, but not touching it. So we do actually have an asymptote along the y-axis, and it makes sense because remember, a over x plus q, x cannot be 0. So my vertical asymptote, x cannot be 0. My vertical asymptote is where x is equal to 0. So your domain, the graph exists for all of the x values going to negative infinity that way, all of the x values going to positive infinity that way, but it cannot exist here where x is equal to 0. There's your domain. Your range, very similar. It's not x, remember it's range, it's y is an element of all the real numbers, but where, if you go along the y-axis. So another good piece of advice is take your finger, run it up and down the y-axis. So the graph will exist for all the negative y values, all of these values, all of these values, all of these values, but not here. Not here, because we've got an asymptote. So not where y is equal to 2. That's this line over here, this dotted line. Not where y is equal to 2. And then again, the y values exist once more, all the way up, 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 up. So an equation for this function, for example, could be y is equal to 1 over x plus 2. The plus 2 is your q value. That is your horizontal asymptote. And when you state your range, you have to say that y cannot equal whatever that value is. So here's one last example of the hyperbola. Again, my domain, the same, because x cannot be 0, because if x is 0, it's undefined. And then your range, y is an element of all the real numbers, but y cannot equal negative 3. Again, y cannot equal whatever the q value is over here. The exponential function, this is the equation for the exponential function. Q is once again a horizontal asymptote. So in this example, let's say, for example, this graph is y equals 2 to the power of x. We can see that the q value is plus 0, which is why it's not shown here. So my q value is plus 0, which means my horizontal asymptote is where y is equal to 0, this dotted line over here, which is basically the x-axis. The domain for this function, quite easy. Remember, the arrows mean that the function is continuous. It'll extend for all the negative x values and all the positive x values. So therefore, x is an element of real numbers. That's it. X is an element of real numbers. There's no vertical asymptote that's stopping us. Range, however, as you can see in this function, and as we mentioned, there is a horizontal asymptote over here, which prevents the function from going beneath the asymptote. Now, what that means is that there will be no negative y values. So the y values will only be where y is bigger than whatever this asymptote is here. So in this case, the asymptote is at where y is equal to 0. So my y values will only go from where y is bigger than 0, not equal to, just bigger than. So that's how we would write the range. In this case, slightly different function. We have now got a q value that is at plus 1, which means that the horizontal asymptote has moved up. The graph has shifted up 1 unit. The horizontal asymptote is now where y is equal to 1, which means the graph does not exist there. So the domain, same thing. X is an element of all the real numbers. Range is from where y is bigger than 1. That's it. Here we've got a slightly different function, as you can see, because our a value is negative. It's almost like the graph reflects, it's beneath the asymptote. Just take note that when the a value was positive, like here, the a value is positive 1 actually. It's invisible here, invisible 1. Remember, 2 is the b value. It's above, the graph is above the asymptote. Same thing with our first example, the graph is above the asymptote. Here, our a value is -3. So our graph is below the asymptote. So slightly different scenario. Our domain is still the same. X is an element of real numbers. Our q value, our horizontal asymptote here, is still where y is equal to 1. But now the graph is below that. So what it means is that the graph will approach. It'll come up like this. It's increasing. It approaches this asymptote. It never touches it. It never crosses it. It never goes above it. So what this means is that the y values for this function is where y is less than 1. Not greater than, less than. Because here, all of these y values that exist. And that's how we write it. I hope that this has been a helpful video. Please check out the rest of my function videos and other math videos. Check the links in the description box below. Subscribe for more videos. Can't wait to see you in another one very soon. Bye, everyone.